Hello. Welcome to this HEEDS Quick Start video, devoted to the topic of the SHERPA search framework in HEEDS. With this video, we assume you are already familiar with the product called HEEDS, and perhaps you even leverage it already to discover better designs faster. Today we will showcase an illustrative scenario of utilizing SHERPA, the primary search strategy in HEEDS, for virtual mountain climbing to discover the highest peaks in a given territory. In doing so, we will explain the governing search techniques inside the SHERPA search framework, so you can better understand how to benefit from its advantages in your real engineering challenges. At first, however, let's briefly recap how the HEEDS product line helps us against our motivation for the topics at hand. Recall, HEEDS has 4 foundational enabling technologies at its core. Process automation allows for the auto-generation of the data using direct interfaces, or portals, to common CAD and CAE solutions. By chaining tools together in a process with seamless data transfer and connectivity between tools, HEEDS is able to replicate an engineering workflow in an automated fashion. With the software automation prescribed, distributed execution allows for the designation of the appropriate software licensing modules and hardware specifications to attain maximum throughput of the data generation within the automated process. Whether running locally, on an HPC, or in the cloud, HEEDS makes it possible to rapidly configure a workflow to your hardware resources. With a fully defined automated workflow and link to the designated hardware, the next enabling technology is the efficient search component of HEEDS. This is the piece of the technology that allows for the data generation against goals, with the latter against goals part of the statement being the focus. With state-of-the-art search technology, HEEDS is able to rapidly generate data of value against the intended performance goals. It is this area that we will focus on today. And finally, as noted previously, the leverage of post-processing techniques on a common platform is also key to the value HEEDS offers. This data interpretation component is what we term insight and discovery. The focus of today's Quick Start video revolves around the efficient search pillar. Specifically, we are focused around iterative learning as it pertains to optimization. Within HEEDS, we have a proven solution for meeting innovation goals which is easy, reliable, and efficient. The SHERPA search framework is a hybrid, adaptive approach to optimization, which leverages various optimization algorithm techniques and strategies simultaneously. With the unique, proprietary methods it deploys, it has been proven to solve a wide array of problems, doing both global and local search simultaneously. In doing so, it is able to overcome the typical challenges associated with optimization with a singular algorithm, by blending the strengths of various methods and algorithms in a unique way. This is the hybrid aspect of SHERPA. Additionally, SHERPA is adaptive in the sense that it tunes itself to the design space as it runs. It learns about the landscape and in doing so, in real time alters how it searches the space. It is this adaptive nature that allows it to uncover innovative solutions faster and against a singular user input, that being the design budget. On top of all of this, the SHERPA search framework is extremely simple to use, eliminating the need for variable screening, upfront design of experiments, model simplification, manual iteration, algorithm selection and tuning, and many of the other historic challenges associated with optimization. In practice, SHERPA works to find the best combinations of variables to attain your goal, set by the user-prescribed objectives and constraints. In this diagram, our goal is to be as low on the y-axis as possible, within the prescribed budget. The budget here is represented by the maximum allowed number of designs on the x-axis. Upon launching the optimization, SHERPA goes about navigating the design landscape against the prescribed budget with automated exploration. As noted prior, SHERPA is robust, efficient, and easy to use. It is a key part of the HEEDS solution, and the catalyst for discovering better designs faster. With that backdrop for today's focus area, let's look at an exemplar, non-engineering problem to understand how SHERPA works. As searching a design landscape is very much like navigating a mountain range, where there are different terrains, cliffs, hills, peaks, and valleys, whereby each range is unique, we thought it a good idea to explain SHERPA within that same context with the problem shown here. To demonstrate, the challenge we are solving today is to find the highest peak of a mountain range, or a given design landscape, within a prescribed evaluation budget. We can then review and discuss the search history to understand how SHERPA's hybrid and adaptive nature explores the design landscape. As mentioned, we are striving to discover the highest elevation upon a given map, as the key objective of our design space exploration today. The varying input parameters for this problem are the global coordinates of the Earth, commonly known as longitude in the X direction, and latitude in the Y direction. The map for our virtual mountain climbing tour is provided by the website www.opentopodata.org, and we utilize its open-source RESTful API for automating the data exchange between the online map and HEEDS. Before going to HEEDS itself, let's illustrate the engineering problem in this next section. Let's start our expedition at the birthplace of SHERPA, nearby the Red Cedar River in East Lansing, Michigan. From here, we leave the relatively flat lower peninsula of Michigan to stop by a more mountainous region around Lake Garda in Italy. This picturesque landscape illustrates various scenarios that may easily occur in your real engineering applications as well. This angular view shows us a large mountainous territory, with mountain peaks in white color on the upper area, totally flat plains in the lower region of the view, and relatively narrow transition zones, with rolling hills in the middle of the screen. Furthermore, the mountain ridges shown are oriented in many different directions, and divided by either steep cliffs or wide-open valleys. If we make a hypothesis that this landscape represents typical engineering goals, like design efficiency, manufacturing reliability, or product life, just to name a few, we can immediately see that it can be very tricky to discover the top-performing designs, represented here by the peaks or valleys in the analogous mountain range. Higher dimensionality, or number of variables, to the problem complicates things even further. Moreover, spending a lot of computational resources in the flat country, analogous to poor-performing or non-innovative solutions, is obviously inefficient relative to time and cost. Another frequent difficulty in real-life engineering problems are unpredictable areas within the design space caused by erroneous design evaluations during execution. We can imagine the Blue Lakes in this view being such erratic zones, without any result for elevation height in the Z direction. It becomes evident that an optimization algorithm needs to be able to do both: cope with error designs, and invest computational resources smartly in promising realms of the design space. This is exactly what the SHERPA search framework does so remarkably well. It searches tough design landscapes of any dimensionality, including nonlinearities, discontinuities, steep cliffs, or wide valleys in between local optima, in a very efficient way. In addition to its technical supremacy, it is also very easy to use for any application engineer. Having said this, we want SHERPA to demonstrate this in action now. While the current design landscape in this view looks pretty interesting, we do want to make it even more challenging for SHERPA, and for that purpose we go east further on the globe, to the very mountainous country of Japan. In Japan, we zoom in to the main island Honshu, and right in the middle we will find one of the most iconic and most famous mountains of the world. Mount Fuji, the tallest mountain in Japan, with an elevation of 3,776 meters, was added to the World Heritage List in 2013. The big question is, will SHERPA be able to discover Mount Fuji as a small dot within the much broader segment of the main island of Japan. Mount Fuji has just one single peak with the elevation previously cited, representative of an innovative breakthrough in our engineering world. This is our goal: to climb Mount Fuji vertically. Implementation of today's problem into HEEDS includes the following steps. Firstly, we zoom out from Mount Fuji to capture a much bigger territory of Honshu Island to encapsulate our design space. Next, we have to transfer the marked segment as parametric space into our simulation models. For reference, we can see in this high-level view the parallels of latitude and meridians of longitude. The same grid lines will be displayed in HEEDS later on. This brings us to the HEEDS user interface for a review of the process setup and the optimization study settings. Here, the Python portal is utilized to establish an automated workflow between HEEDS and the RESTful API of the online map provided by the website www.opentopodata.org. The global coordinates of the online map are represented by the variables latitude and longitude. The online map then returns the respective elevation for a given point, which is subsequently stored in HEEDS as the named response elevation. HEEDS will seek to identify the relationship between latitude and longitude relative to elevation to explore the design landscape while seeking to find Mount Fuji. Worthwhile mentioning are also two image files that are listed in the Visualization tab of the Python analysis. The image, lock.png, shows the single location of a given design point, and the second image, alllocks.png, depicts all design points that have been explored along the study up to the respective design point. These images will be available directly from the web page inside HEEDS post for interactive discovery and interpretation. With the process automation setup complete, we can look through the study settings. We start on the Methods tab and see that the hybrid and adaptive method SHERPA is leveraged for this optimization study. Here we've set a total number of 100 evaluations for the search budget within the methods properties. Please note, no additional study settings are required for SHERPA search framework, making it practical and easy to deploy amongst designers and simulation engineers. The objective of the optimization study is maximize the response elevation, as shown here. Constraints are leveraged to ensure optimized solutions meet the performance requirements specified for the product design. Here we've added constraints for visual support. A lower constraint limit of 2,500 is specified, such that any higher peak discovered will be highlighted as a so-called feasible design, while all other designs below this limit are classified as infeasible designs. The SHERPA design space exploration is now ready to be launched. After execution of the study, the Run tab provides a very structured summary of all relevant information. As shown under the study details, 100 evaluations have been executed, and of these 100 designs, SHERPA discovered 10 feasible designs, in this case indicative of finding 10 designs with an elevation above 2,500 meters. By the way, there was also one single error design. It can easily happen during study execution that something goes wrong with individual simulations. SHERPA simply ignores such designs and moves on in the search, noting that it should not explore that particular design variable combination again. For more insights and discovery of the design study results, we now move to the HEEDS post-user interface. This plot view includes a design table on the top left, along with an objective history plot of the elevation response on the lower left. The much larger model image on the right-hand side shows the location of the current design within the map of Japan. While Mount Fuji is visible as a white peak located in the south, just a little bit right of the center, the location of the first design is very far away to the north. By stepping through the first couple of designs, we can observe a pure discovery phase, where the global search methods of the SHERPA search framework are placing designs across the entire design space. As we continue to add more designs, the history diagram in the lower left corner indicates an already increasing and thereafter improving elevation response. As a reminder, the solid line in this diagram represents the history of the best design found at a given time. Design number 11 does already have an elevation above 1,000 meters. So, during this initial phase, SHERPA could already learn about the design landscape, and as we continue the global exploration, even better designs above 2,000 meters are discovered. Let's stop the animation for a minute to explain the search carried out so far. The elevation history plot now shows several high-performing designs found after the first design above 2,000 meters. We call this phenomena local refinement of promising design candidates, and it is driven by local search methods within the SHERPA search framework. Both the global exploration and local refinement modes of SHERPA are continuously run in parallel. Given the clusters in the elevation history plot, it would be quite interesting to understand the location of those designs. As such, let's switch to a different plot view, including model views with all designs so far. At this point, after around 1/3 of the search, the map shows a pleasing pattern of designs explored thus far. While putting designs across the entire map, we can also see a dense cluster of designs in the Japanese Alps. Just a little bit south of those designs resides a second cluster of designs, and even nearby Mount Fuji, we can see a first design. We can conclude that SHERPA does not follow and learn from just one, but instead multiple promising design candidates. Let's continue the animation to see how the search progressed. After about halfway through the search, SHERPA makes a huge step as it finds a design above 3,000 meters. By looking closely at Mount Fuji in the model view, it becomes clear that a second design was put there, and in fact we begin to climb up Mount Fuji virtually. Let's watch this next exciting stage of the design space exploration, as we explain the search characteristics of SHERPA while we progress towards our goal. For the sake of better visualization, we will switch the plot view for the second half of the search. The new 2D relations plot on the lower left showcases the same design locations as seen in the original model view plot. However, the color coding reveals additional information about the timing of each design, with pink being the initial phase and cyan being the upcoming advancement stages of the study. Additionally, the best design discovered gets a golden circular marker as well. The heat map plot in the upper part of the screen depicts the design count very nicely. Here, the color coding represents low values in green and high values in blue. Having said this, the design space exploration continues for its second half. Shortly after our two high-performing designs nearby Mount Fuji are identified, SHERPA refines that neighborhood more closely with several additional designs, and eventually hits the best design of the entire study, marked with the golden circle. The fascinating part onwards is the interplay between the local refinement mode around several high-performing realms, and the permanent global exploration mode throughout the study. In other words, SHERPA is intentionally designed to never get stuck with local optima, and instead, keeps exploring the entire design landscape until completion of the design budget allocated by the user for the study. As a summary of today's quick start video, we can conclude that SHERPA has done an excellent job to scan the whole landscape globally, and at the same time invest designs smartly in promising regions of the design space. This was possible thanks to the hybrid and adaptive nature of the SHERPA search framework, allowing for iterative learning and flexible utilization of local and global search techniques throughout the design study. In real-life engineering projects, this characteristic translates directly into being fast from the time perspective, and efficient relative to cost and innovation goals. We also remember that we only needed to specify the total number of evaluations for the study, and everything else was achieved by SHERPA automatically. For you as a designer or simulation engineer, this means you can truly focus on product design, instead of worrying about numerical subtleties of optimization algorithms. Simply put, SHERPA is very easy to use and helps you discover better designs faster. By zooming in to the best design found, we can see that SHERPA was indeed able to discover Mount Fuji in this huge territory of Japan's main island. What this means for you on your engineering problem is that SHERPA can help you discover your highest peak or lowest valley, attaining your innovation goals. Additionally, besides finding the highest point in Japan, SHERPA also discovered many more designs around its neighborhood. In our real-life projects, this translates to getting not just one solution, but a series of high-performing design options. With this major advantage of using SHERPA for design space explorations in HEEDS, you will be able to make subsequent design decisions based on multiple design candidates, rather than just one variant. We close with this virtual scenery of Mount Fuji on the screen, and say goodbye from our digital expedition across the globe. Hopefully you are inspired to take advantage of HEEDS and SHERPA in your future projects, such that you can confidently and robustly navigate the design landscapes that constitute your engineering design challenges. Much like seeking the summit of Mount Fuji, SHERPA will help you reach the pinnacle of your innovation goals. See you around, and thank you for watching this video.